Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. This is inshallah the last session of the course. In the last two sessions, we talked about transformers, then CNNs. And at the end of the transformers session, we mentioned that there was some work on processing images using transformers. And this is the short session, inshallah, that we will cover today. Transformers for images. The idea is that we can, in principle, process images as if they are text. If they are represented by embeddings, then we can process images as text. It looks like a nice idea in the beginning, but it is not obviously a promising idea for two reasons. First, images are much larger than text, especially if we talk about pixels. So we can the first idea to think about is to treat each pixel as a token, right? And represent each pixel by an embedding vector. If we do that, then the complexity of the self-attention layer will be huge because the number of pixels is in millions. And you know that the self-attention is computed between every token, right? Between pairs of tokens. The computations of the self-attention weights would be a bottleneck in this case. Another thing is that CNNs have really good inductive bias. They are, if you remember, the convolutional layers are equivalent to any translation. If I made any translation to the image, then the output of the layers will be also translated. But that's not the case in transformers by definition or by structure. Transformers are not meant for 2D structure of the image. They are not by default doing this spatial translation. So we have to learn that using the training data. But nevertheless, with the scale of the model the scale of transformer models and the scale of the data that is available and that you will see inshallah very soon, we can achieve good performance with relative to the performance of CNNs. We'll see. We will discuss three models that are transformer based for images. First, image GPT, and then vision transformer, and then a version of vision transformer called multi-scale vision transformers. From the name image GPT, what do you expect? Okay, so GPT is a decoder-based model, right? It generates what? In the original structure of GPT. Generate tokens, right? Generate next token, right? Predicts next token. So the idea here is that it will predict the next pixel, the next pixel. Okay, that's the idea. So it is a transformer-based decoder. The autoregressive property is that it will now predict the next pixel. Given whatever generated from the pixels, it will generate the next pixel. Okay. The model that was introduced at the time has 6.8 billion parameters. It operates, although it is really large, but it operates on very small scaled images, 64 by 64. Otherwise, the model will be much larger. And if you think about it, each pixel has RGB values, right? And the RGB values are representing the color, and usually it is like 32-bit or 64-bit or whatever. But it was quantized here to be 9 bits only, so that it can be really processed using the transformer models. If that's the case, then each pixel is just it has one value out of 512 values, because we have 9 bits to represent each pixel. Remember, in the transformer, we had vocabulary size, right? It can recognize some tokens, right? Here, the tokens are pixels. And if we assume that each pixel has 9 bits, then the possible values of the tokens here are just 512. Okay? Did you get that? So that is actually the vocabulary that we have. So in processing text, we have to find we have to get the vocabulary set using the tokenizer. Here we don't need any tokenization because we know that the tokens are pixels, and in that specific case, the pixels have values has one value. Each pixel has one value out of 512 values only. The image GPT has, or any transformer-based model that is used for images, it has to learn its own positional encoding at each pixel. Remember, for CNNs, we by default, by structure, we know that each pixel has neighbors, right? And that's how we design kernels to process a region, right? But that kind of 2D region is not known by default by the transformers. Transformers process 1D data, not 2D. So they can understand that yes, this token is the next to the other token, but there is no relation between rows. There is no concept of rows in transformers. So even if there is a pixel that has a pixel at the top of it, they are not neighbors in the transformer when the transformer processes it. So the positional encoding here has to be learned from scratch. These are, I will show you two examples of using image GPT. Remember, GPT, it is predicting the next pixel. Okay, so the first application here is kind of an extreme application. The image GPT model was given only one pixel, which is the top left corner here. So just one pixel. Each image here started with just one pixel that is given to the image GPT model, and then the model generates the rest. Okay, just from one pixel. Okay, because it was trained to predict the next pixel. Okay, so it is autoregressive, so it predicts the first pixel and then predicts the second based on the first, and so on. Okay, do you have any observations on the images here? Do they look normal? Did you like them? They have some strange things, right? They are not random, of course. And this is an image of a dog, right? It's very very clear. This is a cat, people in a garden or something. But even with that, there are. If you look at the details of the image, you will find that there are some things that are strange, very strange, right? And you can compare this technology at the time. This is like 4 years ago or 5 years ago with the technology that we have now, with the image, with the models, the applications that generate images. I think they look much better than this. But that was the very first attempt in generating images. You can even look at some images and you can see clearly that these are not normal images. There are things that are very strange. But remember that these images were generated by given just one pixel. Okay, so having an image that looks something that is familiar is good by itself. So this is called image generation task. That's an extreme. And the other task is called image completion task. In this task, we are giving the model half of the image. So the first row here is what the model is given for each image, and then the model generates the rest of the image. What do you think about this compared to the other? Much better, right? Why? Yeah, so the context, right? The context, it is given a context here that is much larger than one pixel here. Okay, so half the image was good enough to generate different images. Why do we have, by the way, different images for the same input? Yes, so because the generation is probabilistic, right? One of them is beam search, of course. So it can generate, given the same input, can generate different outputs based on the probabilities. Some details. Remember, this is still GPT, so we will transformer. So we will have an embedding for each pixel in the input, and at the output layer, of course, we also have embeddings. So if it will be used for image classification, then we have to have a classification head. So we have to either use CLS, but there's no CLS in that model. We in that model they average the embeddings at the last layer and then add a linear layer and softmax to do the classification. And it was pre-trained on a very large corpus or collection of images, and then fine-tuned on ImageNet. And for ImageNet, they were resized, the images were resized to even smaller scale, which is 48 by 48 pixels. And with that, the model achieved a 27.4% top one error rate. Still much lower than, or much higher than CNNs at the time. But impressive given that the image size was very small. Yani imagine here the image size is 48 by 48. The original images in ImageNet were 200, I think 256. We mentioned that last time, something like that, 256 by 256. This is much smaller. Yeah, okay, 228 by 228. Still, this is much smaller. And to get that number, that was impressive given that it was the first step. Remember the ImageNet history. This is image GPT here, and you can see that it is not the state of the art, right, at the time, but it was the first attempt to use transformer-based models for image processing. Okay, right. Then we will talk about another family, which is called vision transformer. What are the differences here? Vision transformer is an encoder model. It's not a decoder model. It is an encoder model. One major difference is that the encoder model here doesn't take each pixel as a token. It takes patches of pixels as tokens. Okay? And patches are 16 by 16 patches, 16 by 16 pixels. So that's one difference. The embeddings at the beginning, each patch was converted into an embeddings via linear layer before it is input to the transformer, and position encodings also are learned. Here is an overview of the model, and I think you can see it is very familiar, very similar to the encoder models, except that now we have an image, and the image is divided into patches, as you see, and each patch now is transformed or is represented by an embedding vector, and before that we use the linear layer to convert into an embedding vector. But other than that, this is a transformer block as usual, which is the encoder stack. And then I think here the CLS token was used for classification. Okay, so it's very similar architecture, except the beginning we have patches and we have a linear layer before the embedding layer. Okay, so that's not very different so far from any encoder-based model, except the patches. But then the main difference is that if you remember the transformers in the encoder transformer like BERT, how was it pre-trained? What was the task? Yeah. Yes, masked language model, right? And was that self-supervision or supervised learning? Self-supervision, right? Self-supervision. Here, the main difference is that we have pre-training with supervised learning, with labeled data. So they have a very large database of images, 300 million images, labeled for 18,000 classes. Okay, and that's a big difference between Vision Transformer and the previous versions like Image GPT. So it was pre-trained on labeled data. The CLS was used for classification, and these two changes, the dealing with patches instead of pixels and the pre-training on large labeled data, made a big difference in performance. If you remember, Image GPT reached, I think, 27.5. This one reached 11.5. Big difference in performance. and it is now on par with CNNs. But of course, without this supervised pre-training, it wouldn't be that good. It would have been worse than CNNs. So vision transformer is very close to be the state of the art at that time. Okay, you see the difference between image GPT and vision transformer. Image GPT was a decoder model, and vision transformer was an encoder. Lots of labeled data for pre-training, and also processing patches of images within the image instead of pixels. The third version, or the third family that we will talk about very briefly, is a version of a vision transformer called multi-scale vision transformers. If you notice in the previous two models, we use the image as is. I mean, there's no scaling. You saw in CNNs that usually we do downsampling, and that will increase the receptive field. But so far in these two versions, or these two families of models, we didn't do that. In multi-scale vision transformers, we started to see something like that. So we process multi-scale vision transformers, process the images at different scales. We start with very high resolution patches, and then gradually decrease the resolution and increase the number of channels. So let me explain that on this figure. This is the original image. The first thing is to process the image is to divide it into patches, small patches, maybe 16 by 16, and then define what we call a window. And the window will be 4 by 4 patches. So as you can see here, this is one window, that's another window, that's a third window, and so on. So we divide the image into small patches, and then each 4 by 4 patches will be one window. Okay? Now, if you remember in transformers, when we do the attention, do we do the attention over all input tokens or part of them? It is the original idea of transformers. Was it on all tokens, the self-attention? Yes. Okay, so self-attention is computed over all tokens. Here we do the self-attention on stages. So at that stage, which are layers here, and the images that you see here are processed by different layers. So the first layer here will compute self-attention within the window only. So each window, we will compute the self-attention within the patches inside one window. Okay, so there is no self-attention that is computed between patches from different windows. Okay, at that layer. Then in the second layer, we will shift the window boundaries. So as you can see here, this row of batches and this row of batches, they are in different windows, right? So there will be no self-attention weights between them. But then when we shift the window, now they will be inside the same window, and the self-attention weights will be computed among them. So with every when we move forward, the windows will shift, and when the windows will shift, patches that were in different windows, now they will be in the same window, and we start to compute self-attention weights. Okay, so gradually you will see that self-attention weights will be computed among any larger regions. Then the next step is to combine or concatenate patches together. So every 2 by 2 patches within the window, they will be one batch. So they will be concatenated and they will be one batch, and then the window now will be larger because the window is defined to be 4 by 4 or 2 by 2, whatever. But now the batch, as you can see in this part, are larger than the patches before. Okay, so we are doing iterations over 3 steps. First, we define the window over patches. Then we shift the windows. Then we concatenate small batches together. And then we repeat this cycle again and again. Okay, if we do that multiple times, we will end up at the end with just one window, because we are having, over time, we have smaller number of batches. So at the end, we will have just one window, which means that we will compute the tension over everything at the end. So these are layers. This is a stack of layers. Okay, so you can see that each layer is processing the image in a bit different way. And let me emphasize here is that the input to each layer is not an image, but this is just the structure of the image. Of course, we are processing, we are computing values over different layers. So the input is not the original image, but the output of processing the image from the previous layer. So that's kind of the main concept of shifted window or SWIN transformer. So it divides the image into patches, and the windows are shifted, and the scale is reduced over time. No CLS token was used. The averages of the embeddings at the end is used, and the performance here was a little bit better than the vision transformer. So it was I think 11.5. Here it is less than 10, and you can see that there is some improvement over the vision transformer. Here we almost reached the state of the art. And these are three models that are completely based on transformers. They are not CNNs at all, but they showed performance that is on par with CNNs, although they were not originally designed to process images. Okay, so these are three examples of processing images using transformers. Any questions? I know that we didn't dig deep in the details, but this is just a quick introduction for you to such models using transformers for image processing. Questions? Okay, with that, I think we are done with the course, and I hope that this course was really a spark of deep learning in your career. I hope that you will learn much more than what we covered. So let me in the next slide, which is the last slide, really show you where you can go from here. So what's next after this? What we covered is just 11 chapters from the book. We intended to cover much more than that, or I intended to cover much more than that, but the time was really tight. So we didn't cover, unfortunately, unsupervised learning. There are multiple chapters in the book. If you want to continue, I would recommend especially these three chapters. GNN are special kind of neural networks that are meant to process graphs, and there are lots of real-world data that are graphs. So this is, I think, you should read. And two examples of models that are image generators. If you are excited about how these things are done, GANs and diffusion models. These are two things that I would recommend for you if you want to really read about generative models for image generation. There is also reinforcement learning that we didn't cover, but it will be covered next semester. There is a course, complete course on reinforcement learning. I'm not teaching it, but I would recommend if you really want to continue on this path to take this course or at least audit it. There is also now, since you were introduced to a good level of detail to large language models, I would recommend more readings on that very hot topic. There are two books that I recommend that are very recent. The first is called Hands-on Large Language Models, and the second, Build a Large Language Model from Scratch. And both are, by the way, available freely through the QU library. So they are available, and I checked them and I got them already. Okay, and they are very easy to read, especially that now you have good, I think, foundation on the basic concepts. There is also a course about data science next semester that I am teaching, inshallah. It's not it's not on deep learning, but I think it will make your statistical background, I think, much better for deep learning and for machine learning in general. There is also another course that I might teach next semester, which is, so the data science is an undergraduate course. Information retrieval is a graduate course, and you are welcome to attend. Information retrieval is about building search engines. And I think this is now very, of course, it is important always, because we use search engines a lot in our lives for for long time. But also, especially now, it is important because it's very well connected to large language models. There are lots of online resources for deep learning. I'm sure that you are familiar with Coursera. There are several specializations. I think you are in a very good position now if you want to finish any of them. And finally, you need to have hands-on projects. Okay, of course, after you are finished, you finish our course project, but you should always try new ideas and implement them in projects, because that's the main way you are sure that you really understand the material. Okay. Okay, I think this is it. I hope that you really enjoyed the course. I personally enjoyed the course very much. I hope that you did also. Thank you, and Assalamu alaikum.